number 9, okay, wait, no, this is actually 7. So looking at energy now, kind of energy not from graphs, but from data tables. So like some numbers. Numbers mean we probably are going to use a couple equations. The two that we're going to keep coming back to are that kinetic energy from way back when is 1/2 mv squared. None of this rotational stuff. This is translational kinetic energy then. Not transit, translation. I can spell. And potential energy for a spring is 1/2 kx squared. So these are the two we're going to have to keep coming back to. And the cool thing that I think works on all of these, if I recall, is you can use either actually to find out kind of the kinetic energy. And so let's just kind of jump into it. Hopefully this is making sense a little bit. I know the online learning is a little tricky, but let's just go for it. So we have some ideal spring, and there's a block attached to it. No friction. It's horizontal on a table, and we're just given some measurements and find or determine the maximum kinetic energy. Well, kinetic energy, that means do this one. But the cool thing about this is since we have this kind of block on a table and it's just going horizontally, right? And if this is equilibrium is when it's going to be going the fastest because the spring isn't acting on it. And if it's kind of stretched out here to this maximum amplitude, it's going to be all potential. So here it's all kinetic, here it's all potential. And then if it's like smushed, whatever this same amount is, actually, we can kind of go over here. Then again, here it's going to be all potential. But if energy is conserved because there's no friction, I could actually find the potential at the ends, and that should be the same amount as the kinetic in the middle. So you actually have enough values to actually double check your work on it, really. So it's saying kinetic energy, so let's just use the top one. So it's 1/2 m, so the mass is 0.50 kilograms, and then v squared, well, we're given the maximum speed just straight up is 3.9 meters per second. Don't forget to square it. And we said that, or I said that we can check our work by doing this 1/2 kx squared business. So it'd be 1/2, and then our k, our spring constant, is 85 newtons per meter. And we're told that the maximum displacement, that's really the amplitude, how big it goes, recalling those graphs we just looked at in our last video where it'll maybe start here and it goes like that and it goes back and forth. This maximum amplitude is either to the top or the bottom. It's kind of the same height. It's just kind of this x value really for it. So that would be 0.30 meters, and we square that. So in theory, finding the kinetic energy kind of when it's going the fastest should be the same value as finding the potential energy when it stops and the spring is either maximally compressed like it is here on the left or maximally stretched like it is here on the right. So checking this on my calculator, 0.5 times 3.9 and squaring it, I get 3.8 for the first one, and it's energy, so that's joules, actually 3.80. But that actually checks out with this bubble right there. And let's check the other one, this kind of spring potential energy equation. If I do that one, we have this 85 newtons per meter for the spring constant, I actually still get, I kid you not, 3.8. This one was 3.80, this one's 3.82, but they both round to 3.8, so it actually works out. So I could have done it either way. And the cool thing is, as long as you're told there's no friction, that will always work. So if you have the stuff to kind of do it with the kinetic and with the potential, do it both. Check your work. Make sure you didn't screw anything up. So I'll probably just stick to doing one for the future, though, but just keep that in mind that you could have done it the other way. So we have a block. It's on an ideal spring. There's no friction. It's horizontal. Use the measurements to determine the maximum energy. It doesn't say which. We just want to find the maximum energy. That's all it's really asking for. So we can kind of pick our poison here and choose. Well, 1/2 kx squared easier? Is 1/2 mv squared easier? I don't know. It doesn't really matter. We're doing the same thing. We're multiplying three things and then squaring one of them. So let's just use the first one. Kinetic energy is 1/2 mv squared. So that's 1/2. Our mass is 0.48 kilograms. It always has to be in kilograms. And then our velocity is 4.5 meters per second, and we square that. And that should give you a value of 4, wait, did I do something wrong here? 0.5 times 0.48. Oh, yes, that's what I did. I forgot the point in my 4.5. I actually got 4.86 joules. Well, that would round best to 4.9, kind of sticking to our 2 sig figs rule here. And let's just for fun, let's try the spring one. If we're doing 1/2 kx squared, that gives us 1/2, and then our k is 85 newtons per meter. And then our x value is 0.34 meters. Don't forget to square it. That should actually give us 4.9 still. Let's see if it does. I get 4.91 joules. So these two are not the exact same, but they round to the same answer. So you actually still could do it either way. Now this next one, and I think we have 2 left. A block attached, same thing, same setup. There's no friction. Block on a spring. Find the maximum spring elastic potential energy. So really it's saying find the potential energy. Now, again, we can do this using the kinetic as long as you know energy is conserved and we're not losing it due to anything here. But let's just plug in and kind of do it this way this time. So this is probably a little more tried and true with what they're looking for. And if, I don't know, the numbers were slightly off enough and you did the kinetic and maybe a decimal point was a little different, maybe it would kind of screw things up. So my spring constant, we have 85 newtons per meter. And our x is this 0.30 meters. Don't forget to square it. And I get for that a value of 3.825. Well, wait a second. That looks familiar. This actually was number 1, the first question. We were given the same exact value as the very first question here. This is the same numbers, and that's why we got the same answer. The first question is really just expecting you to do it this way, and the second one's expecting you to do it that way, but we already did it that way, so kind of neat. And then we're trying to find the maximum kinetic energy of a system again, and we're told that it's frictionless. That's actually pretty important. If it wasn't frictionless, you would end up losing energy as it slid back and forth. So you would have a difference then if you started out when it's all like maximally stretched. So maybe it's like over here at some later point. If you start it here and then, or actually let's say that this is our equilibrium. If you started it actually over here and there was friction, so it's like a little rough right here, you actually would have a greater amount of potential energy right here than you would have kinetic right here, because you'd lose energy due to heating the bottom of the block and due to heating the top of the floor, and so, but luckily we don't have that. That's not the case. So it's asking us to find the maximum kinetic energy. So let's use the kinetic method for it, mv squared. So that gives us 1/2. Our mass is 0.50 kilograms. Our velocity is 0.34 meters per second. This actually also is a repeat from one of our earlier questions, but let's just go for it. Maybe you saw that, and maybe that made this easy for some folks. So I have 0.5 times my mass of 0.5 times my, oh, that's not my maximum speed. My maximum speed is 4.5. 4.5. So that gives me right at 5.06 joules. That would round right up to 5.1. So hopefully that made sense. Let me know if you have any questions.